So we have, are you recording? Okay, so it's a pleasure to have David Schuster give a seminar here. So David, I think did a PhD at Yale, right?
Yep.
All right. And he did very important things in superconducting qubits. And then then he moved to Chicago. He has a big group working on superconducting qubits and doing all kinds of great stuff. Won a lot of honors and prizes. You got the Packard, right?
Yeah.
Fellowship and other notable things. And today he's going to tell us about.
Can I just interrupt?
Yeah.
I'm sorry for interrupting, but I just have to mention that David Schuster is one of the pioneers of the transmon qubit, and you have to mention it because it's like the most popular superconducting qubit. And sorry for interrupting. I just had to mention that. That's important.
Yeah.
As far as I'm concerned, at least. All right. Sorry.
So yeah. Mm-hmm. Thanks for this. So David, the floor is yours. So you tell us about building photonic materials, right?
Yep. Yeah. Great. Well, yeah. Thank you for having me. I really wish I could be there in person. It would be really nice. But anyway, we'll do it. We'll try it virtually and see how it goes. So today I'm going to tell you about building synthetic materials, in particular with microwave photons. So there's lots of ways you can do it. So conventional materials we usually think about in condensed matter are solid state materials, and usually the particles that are sort of doing the action are the electrons. And the exciting things happen when you start to see electrons interact with each other. Another platform where you can try to simulate this kind of system is ultra-cold atoms. And there you typically have interacting atoms in an optical lattice or perhaps in a tweezer array or something like that. And that's also a very nice platform. But today I'm going to talk about another platform which I think is a little bit less well developed, which is sort of to use photonics for this purpose. So here we'll have photons being the things that are doing the interaction, and you could do this optically, and there are groups that are doing this. But the way we do it is our photons are microwave photons, and we use superconducting circuits or 3D cavities as kind of the substrate for that. So I'll tell you a little bit about why that's interesting. So you might say, why should you use microwave photons instead of any of these other things? The other platforms are also great and good at things that they do, but microwave photons are nice because they can have very long photon lifetimes, like up to seconds for a single photon in a superconducting cavity, if you use things like what they've developed for accelerator cavities. You can get very strong interactions, so megahertz to gigahertz interaction strengths, and that's on top of just a few gigahertz of total energy. So very large interaction strengths relative to other other energy scales. For example, with atoms, you can also get a second lifetime, but it tends to be more like kilohertz or even hertz dynamics, depending on which platform. And the other thing you get, which I think is perhaps the most interesting piece, is that you get wires. So when you make a circuit, you can connect things in all kinds of crazy ways. You don't have to just have a physical lattice, for example. And so Andrew Hauck is doing some really excellent work in that regime, and we also do some things there. You also get some nice tools for exciting and probing things, but there are some challenges too. So perhaps the main challenge is that you start with nothing. You basically, literally nothing, in the sense that photons are intrinsically lossy. They're unlike electrons or atoms. Their number isn't conserved. They can just get absorbed by the walls. And so even the question of how do you populate a many-body phase, regardless of how interesting it is a bit of an open question, and one which we'll talk about today. but and as well as, you know, they don't interact with magnetic fields, they don't interact with each other. So we have to build all of these properties. But if we build all these properties from scratch, we'll have control over them. So that's sort of the nice thing. So the first part of the talk will be kind of how do we get these photons to interact, and how do we build something that approximates what's called the Bose-Hubbard model, which I'll explain in a minute. The next thing is how are we going to solve this problem about photons decaying? How can we make it so that in equilibrium there want to be photons and not just vacuum? Then we'll talk about how we can make synthetic fields, magnetic fields for photons, so that we could potentially explore something like you know, quantum Hall effect type dynamics. And then lastly, we'll talk about creating a blockade, but instead of like a Coulomb blockade or something, it'll be a photon blockade. Okay, so to start with, let's talk about this Bose-Hubbard. So this is a very common model for interacting bosons, and it's thought to, you know, be kind of maybe the simplest model, or the most, maybe it's not a simple model, it's very rich, but a very basic model that gives you a lot of the physics of superconductivity. And so there's a couple components. So the first one is over here, and it's an energy term that's proportional to the number of excitations. So you can think of that like a harmonic oscillator. And you have a lattice of these sites, and then they can hop, these particles can hop from one site to the other. So that's this term here. So you take a particle away from one site and put it on another site. And then one of the key bits is that these particles should interact. So if we put two of them on a site, we get an energy. It's different than having just one at a higher excitation. So that gives you this n squared term. And so the energy scales here are the overall energy, then there's the interaction energy, and then there's the tunneling energy. And so one of the big predictions of this model is that if J is larger than U, then you get a superfluid phase. So the phase is well defined, but the number is not well defined. But if J is less than U, then these interactions make it such that there wants to be exactly one particle per site, or n particles per site, depending on how it's tuned up. And interestingly, we'll see this is true whether it's an attractive or a repulsive interaction, either way. And so we'd like to, so in this first thing I'll tell you about, we're going to explore this physics. So the question is, how do we realize some, you know, kind of this abstract Hamiltonian in circuits? And so the first circuit we have that probably everybody's familiar with is a harmonic oscillator circuit, which for a circuit is the LC resonator. So an inductor and a capacitor. And quantum mechanically, it just looks like a harmonic oscillator. And in our case, we're going to do it at microwave frequencies, so about 5 gigahertz. And so the way you can think of it is, you know, adding one photon is h bar times 5, or h times 5 gigahertz, and two photons is another h times 5 gigahertz. But this is a linear circuit. It doesn't have those interactions, so we can't make the model just out of that. We need another element, and that's called a Josephson junction. And the Josephson junction looks to first order like a nonlinear inductor. And so this is what it looks like physically. It's about 200 nanometers by 200 nanometers, and it's just a little aluminum oxide, aluminum overlap. So there's sort of two fingers of aluminum, and there's a very, very thin layer of oxide in between. And that now, it looks like a nonlinear inductor. So now, instead of equal energies to go up, there's actually a little bit less energy for the next one, and a little bit, each time you go up in photon number, you have a little bit less energy. But it's actually, in some sense, a lot less energy because it's much more than a line width. And so it's a very nonlinear system, and this is going to give us our U. So in this case, like the U would be 300 megahertz, because that's the difference between here and here. So adding an extra photon means that you get, it actually costs a little bit less to add the second photon than it did to add the first one. Okay.
David, can I interrupt?
Yes, sure.
So a simple questions on the linear LC resonator. When people say I put one photon,
yes,
and I think about the field being there is of course the field in the capacitor and the field in the inductor, right?
Yes.
So where is this excitation? Is it in the capacitor or inductor? If I put like one photon,
it's oscillating back and forth. So you could think of like the capacitor as like the momentum, and the inductor, the electric field is like the momentum, and the magnetic field is like the position in some sense. So they're conjugate variables in that sense. And you can think of it as almost, we like to think of it as this fictitious particle of where the position is sort of the flux in the inductor, and then the momentum operator then becomes the charge in the capacitor.
Okay.
But the math is exactly the same as as x squared plus p squared, but it's just flux squared plus magnetic flux squared plus q squared. And so it's like flux squared over 2L plus charge squared over 2C is sort of like the equivalent of p squared over 2m plus m omega x squared. Yeah. Is that helpful?
Okay.
Yeah, and like in terms of like the currents, basically, just like in a regular LC, you can think of an excitation as, well, a coherent state at least would be like the thing that you normally think of as sloshing back and forth of the charge between the capacitor and then going through the inductor and then back. So that would be a coherent state. Okay, so yeah, and so so there's another type of interaction we're going to use in this talk, which is what's called circuit quantum electrodynamics, and this is another Hamiltonian, which is again, another kind of relatively simple Hamiltonian. You've got a harmonic oscillator, right, and that's basically the cavity, which is going to be something like an LC, or it could actually turn out to be any kind of electromagnetic mode. And then there's the a qubit, which will have, you could think of it as like a spin, or anything anharmonic would work as well. And then there's this interaction term in which you can take a photon out of the atom or the spin or the qubit and put it into the oscillator, and then it will coherently oscillate back and forth at this rate. We're going to go into a limit where these two systems are off resonant, and so you don't get oscillations, but the sort of virtual oscillations give you a second order term, which looks like an energy shift chi, which is proportional to the number of photons in the cavity and the state of the qubit. And so, and you can, if you look at the cavity, what you see is that there's two possible peaks depending on whether the qubit is in G or E. So this is raw data, and this is sort of how we do our measurement. So if the qubit is in G, the peak is over here, and if the qubit is in E, the peak is over here. So if we measure over here, we will we'll see that it's either a zero, like if we get transmission, we know it's in the ground state. If we don't get transmission, we know it's excited. So that's how all of the measurements are taken in that way. And these are separated by two chi. And then, but also you can look at this term the other way. So if we actually measure, instead of measuring the cavity, if we measure the qubit, then we can actually count the number of photons in the cavity. So there's 0, 1, 2, 3, 4 photons in the cavity, and you see you get a Poisson distribution if you put in a coherent state. And those peaks are also split by 2 chi. So this type of an interaction lets us, really manipulate both the qubit and the photons in the cavity. So we'll use that later.
What determines the line width in this plot?
So the line width of I think in both of these, it's going to probably, in most cases, it will, well, it's kappa. In this case, it's the kappa of the resonator, it's the decay rate of the resonator. In this case, it's the minimum line width, like it's sort of the mean number of photons times the line width plus the intrinsic line width of the qubit. And to that point, for people who are in the know about this stuff, there's one number, if you want to know like how good this is, like kind of the ratio of these things, you take the sort of coupling strength squared and divide it by the two decay rates, and you get a number. And basically, if that number is larger than 1, you're in what's called a strong coupling limit. And so this was a big goal for a while, but now we're at 1 billion. So like, I mean, we're like really deep into this limit, and that's, I think, one of the special things about this particular platform. So like, for example, in atomic physics, you can also do this, but it's even getting to 1 is a pretty big challenge, and maybe people have gotten to 100 or 1,000 or something, but 1 billion is really is way out there. So that's one nice thing about circuits. Okay, so what are the sort of physical ingredients? So we need macroscopic artificial atoms. We need like these qubits. So this is an example of what one looks like on a stick. So they're actually pretty big. So you can see like this is 3 millimeters. It's sort of not that on my screen. It's about real life. If you zoom in, there's a small part, but most of it's actually pretty big. And you can literally just put it on a stick and stick it in a box if you want. These things operate at cell phone frequencies, and we use cell phone test equipment basically to control it. And so you get a big rack of electronics. And to put this into kind of temperature units, like so 5 to 10 gigahertz is 250 to 500 millikelvin. And so we'd like to be very cold compared to that. So we go into a dill fridge at 10 millikelvin. And so you see, so this is the cryostat. And when people show you pictures of quantum computers, really it's usually just a picture of the cryostat. The actual, interesting quantum bit is like somewhere inside one of these cans. This has 2 samples in there. And all of this stuff is wiring and filtering and things like that. Okay, so so now now that we have our components, we can start to build our lattice. And so our lattice is going to be an array of these qubits. So each one of these little pluses is a qubit. The thing that you can see, the plus is like the capacitor. And then if you zoom way in at the bottom there, you'll see that there's this little structure here, which is a junction, which is split into 2, which allows us to then tune it with a magnetic field. So we can basically change the energy. So that lets us tune sort of the epsilon in that Bose-Hubbard. And that's important because unlike atoms, every qubit's a little different. And so we need to so we start out with a fair bit of disorder. And so this knob lets us tune everything to get rid of all that disorder. And we can also do this quickly, and that's useful for readout and for other things.
So the magnetic field is tuned per qubit? You have like a small coil for each qubit? Yeah,
exactly. Yep.
Okay.
Yeah, it's lithographically on that chip. So, and then we also have a readout that works for each qubit, although it's frequency multiplexed to one line, so we can measure each site. And then we have these extra pieces, an extra drive line and a special cavity that's much more strongly coupled, which is our reservoir, and we're going to use that for being able to stabilize the system. So that'll be
the drive line is only coupled to the first qubit?
Yeah, the last qubit. Yeah, yeah, this one's just coupled. So this qubit we're going to sort of use as a special site. And you can also see if you squint that the coupling is a little bit different between these two than the rest of them. And that's a detail which is relevant. But okay, so this is our chip that we're going to be using, and complexity-wise, I would say this is one of the more complex chips that's in an academic lab, but it's nothing particularly crazy for a company. Okay, so. Now we kind of need to just figure out all these energy scales. We want to find out what are the different energy scales we have in our Bose-Hubbard thing. So to do the U, we basically, if we just measure the qubit, we'll see there's a 0-1 transition, and then there's a 1-2 transition. And so by just looking at the difference, we can just directly read off the U. If we put a photon in one site and then we look at it oscillate back and forth between its nearest neighbor, we can read off the J, and we can do that for each site. So we can do that. So this frequency corresponds to J. Another way of getting the J is you can just do lattice spectroscopy. So these are the modes of the lattice. So this is like, in some sense it's the band structure, but it's discrete because there's only a few modes. And then the other important piece is coherence, like how long do we have for the system to stay quantum, essentially. And you can kind of see here that that's like of order, maybe tens of microseconds.
This is a single qubit kind of coherence?
This is a single qubit in this case, but we do all of this for every qubit. So,
so again, maybe I missed it, the interaction term, where does it come from? How do they interact?
So if you see here that like these qubits are just next to each other, and so there's some capacitance between them. And so that capacitance gives you an interaction in which basically the electric field on this one can excite the electric field on that one. So a photon here can hop over to here. And it's exactly, well, with a rotating wave approximation, at least, it's exactly this like, A dagger plus A dagger A type interaction for nearest neighbors.
And this is tunable?
In our sample, it's not, because it's just fixed. It just comes from the geometry. One can make it tunable. Like, for example, in the Google processor has essentially the same architecture, but they make every other for example, if you detune this transmon, then these transmons can have can virtually hop through this detuned one, and then you can make it tunable. So if you're willing to have half as many sites, you can make it tunable. So in this experiment, we don't make it tunable.
Okay, thanks.
Yeah. So we do these experiments that I just showed you on every site, and then we can pick out all these energies. So the energies for the interactions are 250 megahertz. The J's are 6.5, and then the loss rate is way down at 4 kilohertz. And then there's also the disorder is, we think we can get it to less than 100, and dephasing is even less than that. So and so what's key here is just to get this hierarchy, and this is actually kind of the hard thing for most things. Is for each new physics you want to look at tends to you tend to want to have like another level in your energy hierarchy, and so basically how much room you have between your top energy scale and your disorder or your loss is sort of a key metric. But you can see here we have sort of an order of magnitude between these two, so we're pretty deeply in the mod insulator regime, we think. We should be, and then all the loss is like way less than that. It's 2 orders of magnitude away. So that's good. Okay, so now if we want to, now the problem is though, we've made this beautiful Hamiltonian and this great circuit and stuff like that. But the problem is if we, the ground state of this system is not some interesting many-body state. It's not, it's just vacuum. Because if we just leave it there, the photons will be absorbed and the temperature is 0 and they'll go away. So the question is, how can we make it so that in sort of equilibrium in some sense, there want to be photons? So, and so let me show you in a cartoon sense, and then I'll show you how we actually do it. So there's an engine. So we imagine that we have a special site, which is engineered so that it always has 1 photon, exactly 1 photon. And so with that 1 photon, then if we coupled it into the lattice, then it will hop. But we said this is a magic lattice site that always wants to have 1 photon, so a new photon will magically appear there. And the photon that's in the lattice will keep hopping around, and eventually the nearest neighbor will be empty again, and so the photon will hop in. And so this will keep happening until the whole thing is full. Okay, once the whole thing is full, then it turns out that it can't fill anymore because the energy is at the wrong point. Like it wants to put in this much energy, but in our case the U is negative, so it's actually got too much energy. But there's no state there for it to hop into that has this much energy. And similarly, if this guy tries to hop, it also has too much energy. It can't do it. So, and so this is so this will stop. This process will stop, and you'll get this n equals 1 mod insulator state. And it's insulating because when there were holes, things could move around. But when it's full like this, now it can't move because rearrangements within the system are forbidden because you can't have two particles on a site. They have the wrong energy, and you can't add new particles.
David, before you have this multi-insulating state,
yeah,
it's a partially filled system. It's basically, in some sense, okay, it's a small system, but in some sense, it's a gapless system, right? It could do sort of many-body reconfigurations.
Yes.
Then the question whether you cannot have a process where you do some, it's partially filled, you do some, many-body reconfiguration that gives you exactly this difference between the difference you need to actually fill the first excited state and the first lattice site.
Yeah. So yeah, I mean, and this is actually the type of dynamics we'd like to be studying in our next experiment. Yeah, so I will show you some like kind of you know, like a hole doped version of this, and you can see some simple dynamics there. And a thing we'd like to explore is at some stuff at later is things at fixed density, and can you actually, by changing the number of sites, can you drive a transition between superfluid mod insulator, and also being able to measure some of the correlations as well. But anyway, yeah, for now, let me just tell you how we actually make this this magic site, because that was sort of the key bit. So the idea is, so we have our last site is let's say we have 0, 1, and 2 photons we'll look at. And we couple this reservoir, so we put that reservoir there, and it now has a coupling. And we arrange it such that the resonator has a frequency which corresponds to the 2-to-1 frequency. So if there were, you know, so now if we put in exactly 2 photons, and we can do that by, if we drive at half of this frequency, we won't occupy this one, but so we'll either put in a pair or nothing. And so we can put in a pair there. But now that pair can, you know, one of the particles can go hop to the resonator, and then that would make the other one hop down. But then, you know, this decay rate is very fast. So as soon as it hops into here, it's basically gone forever, and it won't go back. And so now it's sort of stuck here. And basically the sort of fidelity that this is in the one state is basically something like the ratio of this time to this time. So if kappa r is much greater than gamma, it's going to be in this 1 photon state most of the time. And so this is what, if we turn on this, if we arrange this and then turn on this drive, you see this kind of filling where it goes up. And I think we've gotten it better since we took that data, but and it was limited basically by, if the resonator is not empty, then you can do the reverse process, and it doesn't work. But if this is, and we had a little bit of occupation there, but
is it also used for cooling? I mean, in principle, it kind of evaporative cooling the hot stuff out.
Yeah, you could think of this as you could definitely do cooling the same way, right? You could basically, you could take one and then put a sideband on that puts 1 photon in here and 1 photon, and then puts it back to the ground state, and then this would decay, and then you'd be stuck there. So you could definitely use it for cooling. I think of this as, in some sense, this is like coherent population trapping or optical pumping, the same way you might do in an atom. But yeah. And in this case, we're trying to stabilize the single photon state. But yeah, it's exactly analogous to that. Okay, so now we can hook up this. That was the single site. Now we can hook it up to the whole system, and we can watch the dynamics. And so what you see is this, and so just to kind of interpret. So this is the site that we're stabilizing, and that's why it never quite it's being driven. So, but then what you see is that it starts out in the ground state, and then there's sort of a wave. You know, you can sort of see those photons kind of spreading throughout the system, and basically by sort of 2 bounces, they've filled up everything, and now everything is, you know, very close to one photon, single photon occupancy. And if you want to plot this quantitatively, it's probably better to take slices, and then you can see here that after about a little less than a microsecond, this is everything is stabilized. And the cool thing is, of course, as long as the drive is on, this will stay this way. So you know, this is you know, I mean, not equilibrium in the sense that it's driven, but in the sense that if you could walk away and come back the next day, and it will look basically the same. So, and again, yeah. So we've been able to make them this mod insulator about 90% fidelity. You know, Nathaniel was asking about, you know, what happens if you have an unfilled one. So what we do for this one is we stabilize the system, but then except for the last one, and then we just bring in an empty site into the lattice. And so this is basically like putting 1 hole in the lattice, and you can actually see that hole, you know, do a kind of a quantum random walk. And so it looks mostly ballistic, right? Now, you may think that this is because of dephasing or something, but actually the dephasing time is several microseconds. So this is actually not dephasing, but it's actually the fact that this isn't like a transmission line. It's more like a semiconductor, and it has a band structure that's like a cosine. So there's actually some dispersion here. And so what you're seeing is that for short times, it kind of looks, vaguely ballistic, but then you really do see that it's a sort of a random walk in this lattice with the cosine band structure. So there's some dispersion there. This happens even in idealized simulations.
How do you couple this? I mean, how do you turn on the coupling to this empty site?
So what we do is we stabilize the whole system, but with one site detuned, and then we very quickly tune it into the lattice. And then you can do the same thing, but now in this one, we turn the stabilizer off. In this one, we leave the stabilizer on when we do this. And then what you see is that it still propagates, but then as soon as it hits the last site, it basically disappears. There's it's not perfectly matched. So you can sort of see a shadow of the reflection, but it's mostly even. So you can kind of see then how, let's say like this were to happen naturally because like one of the photons were to decay. Then that's sort of the dynamics of how it gets fixed. Okay, so now I'm going to switch gears a little bit. So we sort of showed how we can make interactions, and we showed that we could stabilize them, and we could realize this mod insulator phase. Now we're going to go back to sort of, let's say, single photon physics. So mostly non-interacting, although we're going to do strong coupling cavity QED with it. But we're going to try and build a magnetic field for these photons. And so there's lots of ways one can do this, and I've had some great conversations with Nathaniel about this, but and you can do this in a time reversal invariant way. You can do this in 2D and 3D, and you can make all kinds of circuits like this. The one we're going to talk about is actually this middle one, and because if you eventually want to put interactions in, it's much easier to do that if you actually break time reversal symmetry, which these guys don't, and I'll explain that in a minute. But so we're going to talk about this kind of like kind of a lattice quantum Hall thing. And so just to give a little background, so the idea of a synthetic magnetic field is the following. So we all know that if we have a magnetic field and we take, say, a charged particle and move it around, that we acquire an Aharonov-Bohm phase. But the idea of a synthetic magnetic field is sort of take this, and if you do that, you get all this, like in a semiconductor, you get all this nice quantum Hall physics, right? You get cyclotron orbits, and you get skipping orbits and things like that. And the idea of the synthetic magnetic field is to sort of take this Aharonov-Bohm phase really seriously and saying that actually, it's not just that there is an Aharonov-Bohm phase, like when there's a magnetic field in a charged particle, but that is really the essence of the physics. So that if you have a particle that moves around a loop and it picks up a non-reciprocal phase, it's going to behave like it's in a magnetic field. So you can sort of do the reverse, like that if you pick up this phase, you will get these cyclotron orbits and all this stuff. So that's how we're going to get our photons to see a magnetic field. So if we just put, if you shoot a laser pointer through a magnetic field, it doesn't bend, right? But what we're going to do is we're going to try to create a lattice, and we're going to make one of these sites very specially engineered to give it a non-reciprocal phase, such that when it goes around a loop, it picks up pi/2 of non-reciprocal phase. Incidentally, if you compare this to like the amount of magnetic flux, like quanta, that you pick up when going around a lattice site of a traditional like gallium arsenide type sample, right? Because the lattice size is so tiny. Like if you wanted to get that much flux per lattice site, it would you would need like neutron star level magnetic fields. It would be completely unrealizable in the lab. So that's another thing that's kind of.
So what breaks time reversal? Is it breaking time reversal for the photons or for something else?
For the photons, and I'll show you exactly how we do it in just 1 or 2 slides. So yeah. So first, let me show you the non-time reversal breaking pieces, and then I promise I will show you the time reversal breaking piece. So the first thing is, again, so now it's you should think of it the same way as this. It's just an LC circuit like thing, but we make it in 3D and we make it out of niobium. So it looks like this. And so there's a mode that lives in this thing that is going to be our harmonic oscillator. And then for our tunnel couplers, we just have 2 of these guys, and we're going to drill a hole from the back. And so now there's a little hole. So these guys can talk to each other a little bit, and that's what it looks like in 3D. And then we're going to make a chiral site, which is going to have a magnetic element in there. And that's going to be the way that we break the time reversal symmetry. And I'll show you that in a second. And then we'll have a qubit, which will let us do all this cool cavity QED stuff. So those are going to be ingredients. And this is what the lattice looks like together. So this is made out of a single block of niobium. And so these sort of single post sites are the regular sites. These ones with 3 posts are the special time reversal breaking sites. And then out here, there's a qubit that's going to stick in there. So that's what it looks like. As you were asking about the non-reciprocal, how do you break the time reversal symmetry? And so the way we do this, and this is one place where I like to, it's nice to be able to stand in front of the audience and do a silly dance. But the way that we're going to do this is, so we put this a sphere of yttrium iron garnet, which is basically a ferri magnet, so a soft magnet. But you can basically think of it as one big macroscopic spin, a classical spin. And then we're going to put a magnetic field. And when you put a magnetic field, and this 3-post cavity has a couple modes. So there's a fundamental mode, which doesn't really have any kind of XY character. But then there's the next 2 modes. There are degenerate, and it can be polarized along X and Y, kind of like a p orbital of an atom. And they're degenerate, so you can have any superposition. X plus Y would be 45 degrees, or X plus IY would be right circularly polarized, or X minus IY. And if you plot these, circularly polarized ones, they have fields that look like this. And if you kind of stare right at the center here, you'll see that the arrows are basically just rotating in a circle. And so, if we apply a magnetic field to a spin, it will also precess in a circle. And so if the fields are precessing the same way as the spin is precessing, then they're kind of co-rotating. If the other mode of the cavity is going to precess in the opposite direction, and so they'll be counter-rotating, and so they're kind of the interaction is going to kind of average out to 0. And so what you get is so you see you basically get there's 3 modes. There's the mode of the YIG, which is sort of zooming through like this. There's the mode of, and there's a bright mode, which is co-rotating, and there's a dark mode, which is counter-rotating. And an interesting realization, you might think that if you want to inherit the sort of time reversal breaking of the magnet, that you should use the bright mode, and you certainly can use the bright mode. But actually, we prefer to use the dark mode. It's just as time reversal broken, but it's much less affected by it. You can see it's almost flat. So we tend to use this mode, and you can see the crossing here is at a pretty high field. We tend to work down here, and you can see that it's still split. Even it's a little less, but it's actually still split way off here. So we're at maybe a little less than 100 millitesla, and we still get a pretty big gap between these 2 modes.
Why do you call them dark and bright?
Yeah, because this dark mode doesn't, basically you see it's not really, there's not very much of an avoided crossing. There's a higher order mode of the YIG, which does couple, so it does split. I mean, if this were in the simplest picture that I just described, this would just be completely flat across the whole thing, and this one would be split. In reality, like there's some higher order mode that this one does couple to a little bit.
But now everything is time dependent. This is not a time independent system, right?
No, it's time independent. I mean, in the mode sense. I mean, of course, like, right. I mean, when I say there's a photon, it means that there's an oscillating magnetic, electric and magnetic field. So in that sense, it's not. But in the sense that, like, I can think of modes and them having, some particles, like the Hamiltonian of these modes is static.
David,
isn't
can I
it
ask a
driven?
technical question? Oh, sorry.
Yeah.
It looks as if the system is driven, no? But
it's not driven. It's not. I mean, this is just, if I just put some energy in it, and this is the dynamics. I'm not driving it. I just have a static magnetic field, and then whatever field happens to be in the cavity. But I'm not like externally driving it. I mean, when I'm plotted here is like, if I would be like the equivalent of what if I put a coherent state in the system, what would it do? But so that's why it's moving in time. But it's But the system is purely static. I mean, at least in the sense that any magnetic system is static. Right?
But that's like any other circulator of microwave.
Yeah, it's basically like a circulator. I mean, it's really, you could think of this as just a like this is sort of the phase breaking element of that. And if you were to couple into this, system at the right angles, and we've done this, you can make a circulator out of exactly this structure. So if you just, all you have to do is couple, make your input and output couplers in like 120 degrees apart, and you'll get a circulator. And that works. And the only thing that's sort of special about this compared to regular circulator is that it's very lossless. Like a normal circulator might have, 10% loss, and this thing has a Q of 100,000. So that, I mean, but yeah, otherwise it's, you could literally think of it as like inserting a circulator into your system. But figuring out how to make, I mean, like, this is one slide in the thing, but it took like a student like 2 years to figure out how to actually make it in such a way that it really has a Q of 100,000. So,
David, can I ask a technical question? How do you apply the external field? Is that with a coil, or do you put a permanent magnet in there, or because it's all niobium block? So that's
yeah. There's a little tiny rare earth magnet where this little cartoon magnet is.
And there's a hole underneath the Yig sphere?
There's not a hole, it's just really thin.
Oh, okay.
So, I mean, and the surface field of that magnet is like a Tesla probably, so it just goes through. But we arrange it such that the net field is only like 100 millitesla, so it's not hopefully totally killing the superconductor.
And can you tune it, or do you just place it there and just at room temperature calibrate it or something?
Yeah, yeah, everything is calibrated at room temperature and then cooled down. And again, it's not the glorious part, but it was sort of one of the cleverness of the student to get this to work was actually like, how do you tune this thing up at room temperature such that when you cool it down, it actually does what you want it to? It was a big challenge. Yeah. If we calculate the band structure for something like this, so if we just take a strip of this and made it made it long and then just said, and then we say, what is the band structure like of a kind of a strip of this stuff? You can calculate this, and so you can see there's sort of some bulk bands here and here, and then there's edge states on the top and the bottom, and so we can now measure this band structure by. So what's cool about this is like each of these cells is like an inch. And so you can measure each one. We just have a connector on each one, and we have a sort of a big switching matrix. So we can actually measure in or out on almost any site, and we can then measure the band structure. And so if you so for here we take, let's say, the center site, and we just measure transmission there, and like between, let's say, this site and this site, and then you get something like this, and you see. There's these green modes are pretty big, and for the most part, you don't see the red modes or the blue modes. And then if you measure on the edge, like from an edge site to an edge site, you see the ones that are in the edge, and you don't really see the bulk too much. It's you can see a little bit of the bulk in the edge, and vice versa, because this is a very small system. But for the most part, you see the edge and the bulk. And so we can kind of measure this band structure and not just measure the density of states, but because there's so few modes, we can actually just measure every single mode of the lattice. And we can also calculate what we can both calculate, and actually this is measured data. So we can measure the sort of amplitude of the field on every site. And so we can see that, like, for example, this edge mode, like these are the sites that actually have occupation. So it's basically, it's all these sites, and then the gray sites aren't measured, and then for the bulk mode, we can see it's basically localized in the center there. We can also watch this in time. So if we actually hook this up to an oscilloscope, we can actually literally watch it go around. So this isn't actually, so the mode is static, but if we actually put a pulse in, we'll actually get a traveling wave that goes around. So we can just directly visualize those edge skipping orbits.
So David, what is the purpose, what is the role of the actual qubits, the 3 qubits that you put?
So currently there's no, we haven't talked about the qubits yet. So this is all just linear physics. And in fact, this isn't yet single photon. We haven't even put in a single photon yet. So I'll tell you in a second, we have one qubit in there, and what we can do with that is basically show that this actually works for a single photon, and we can actually manipulate the photon state in the system. So I can show you that in just 1 second. So I would say the key thing here is also that this is in this new superconducting system. It lasts for a relatively long time, so about maybe a few microseconds. And in that time, it's gone around many, many times. So you can see, it takes maybe 100 nanoseconds to go around the whole lattice. And so this is kind of key if you really want to see, eventually some kind of, topological many-body physics or something like that. You'd like it to actually go around. And with a lot of these metamaterial things, sort of a dirty secret is that they're usually linear, and like often the loss is like, you have of order 50% loss per site. And so by the time it's gone around the whole system, it's actually decayed by a factor of 10,000 or something. But if you have enough dynamic range and you turn up the power enough, you can still see it. And that would be the case here too. I mean, you notice that this transmission is in arbitrary units. So I claim that because it's decaying slowly, but this is still many photons. So the question is like, what happens if we put in a single photon? But it's hard to know if you put in a single photon or not unless you can detect a single photon. And there's no real single photon, like a photomultiplier or an APD for microwave photons, that you actually need to use a qubit for that. So the way we do this is we stick our qubit in there, and then we have we use a special kind of a sideband. So this lattice has some, is a harmonic oscillator over here, and it turns out if we the excited state of the qubit and the one photon occupation of these various lattice modes will hybridize a little bit. And so if we drive the qubit transition, and it turns out it's better to go, you could in principle go from G to E, but for various reasons, that doesn't really conserve energy. So it's better to go from the third level down. So if you go from F to E, that's a single photon transition. So it's a little bit easier to do. But if you drive it basically at the transition frequency from the F of the qubit to one of the mode frequencies, you can actually put a single photon into the mode or take one out. And so then if you sort of keep this drive on, it'll stimulate a vacuum-Rabi oscillation, an oscillation of a single photon between these two things. And so you can then observe that here. So that's what that looks like. And then if we now what we can do is we can actually kind of do in some sense a similar thing to what we were doing with the band structure, but now with a single photon. So
you're doing like a pi pulse. You're really transferring.
So the x-axis is the frequency of the the lattice mode, which is sort of so it's the difference between it's basically this frequency, and then the y-axis is time. So we just like turn on this drive here, and then we wait, and then after some amount of time, we then measure the qubit. So it's the color scale is the population of the qubit. And so we start out with the qubit in this F state, and then we do an oscillation, and we see what state we end up in. And so what you see is that it's oscillating back and forth. So we start off with the qubit excited, and then it goes into the lattice, and then it comes back, and so on and so forth. So we can put so if we're here, we've put exactly one photon into this lattice. So and so we can manipulate this. And actually, I mean, here we're just putting photons in and out, but we can actually do anything, like any arbitrary control over any of these lattice modes. And you can see here we're also driving pretty strongly, so that these two we've driven strongly enough that these modes are actually hybridized, so that we can actually launch sort of a pulse, like a actual into them, like a spatially localized pulse as well. And we can also measure the photon number in any of these. So if we then now drive the lattice, and then we can now actually use the qubit to count how many photons are in there. So this sort of has like 1.5 photons of occupation roughly. So anyway, this is getting towards the point where we can now do strong. I think it's actually the first strong coupling in a chiral system. But and what we eventually would like to do is to put a qubit on every site. and then basically sort of combine the first experiment that I showed you with this one. And we've done numerics that say that if we do that, we should, that the kind of the stabilized state should actually be something like a new 1 equals 1/2 Lofton state. So we would start to see some kind of a fractional quantum Hall type physics in there.
Would you really be able to kind of go to low enough temperature, I don't know, entropy that you'd be in the
Yeah, so it ends up being, it's basically kind of the line width over the many body gap. And I would say it's, you know, like if with these parameters are sufficient. I mean, not glorious, but sufficient to get there. So assuming we could actually do the same thing, but with a qubit on every site and get all the same parameters, if we don't make things worse, in principle, we should at least see it. Okay, so let's see. There've been a lot of great questions, so I might have to rush through this a little bit, but we could give it a shot, and you know, if we're going too long.
Not strict with the time. So.
Yeah. Okay. So all right. So we've got so the last one I want to talk about. So we now have made you know, we did a complicated thing with magnetic field and stuff. Now I want to talk about sort of, again, this 3D thing with just a qubit and doing cavity QED stuff with many lattices. No magnetic field, but a much cleaner system because we didn't have to deal with the magnetic field. So everything is much more coherent, and we can do some really exotic interactions. So this magnetic field system, I mean, it was strong coupling with the cavity QED, and so in some sense it's very strongly coupled, but we didn't really take advantage of that fact. But in this one, we're going to really take advantage of that to show that we can really do all kinds of interesting many-body physics there. So, okay, so we're going to sort of generalize the idea that we took to make that lattice and say that actually, if you want to make a block of metal that has a mode and a hollow in it, but you want to make it out of a single piece, you don't want to like cut it in two, you can do that by drilling a bunch of holes. So if you drill one hole, it's fine. That hole is evanescent. It turns out if you drill a whole bunch of holes, as long as they don't connect to each other, so if you drill them from the top and the bottom, then you can in the middle create whatever space you want. And so this is a technical detail, but it lets us make very high Q cavities. So this is sort of an example. So even though you can literally see through these cavities, they have the microwave photons can't get out. They're too big. So it really goes to show you these microwave photons are actually quite large physically, right? These holes are like in, I think 3/16 of an inch, and the microwave photons can't fit through them. And we get Qs of like 80 million there. So we can get very high Qs there, as opposed to like, you know, maybe 100 or 200,000 in what I showed you before. So we're going to operate on this thing. So so there's a readout cavity, which is small, the blue, and then there's a long cavity, which has many longitudinal modes that we're going to use. So it's a multi-mode cavity, and there's a qubit that again sticks in between them. So like that, and this is what it physically looks like. It's a, you know, macroscopic object, but it's not like ridiculously large. And so now we can measure those sort of properties. So we can, most importantly, we can measure the coherence time. And so the lifetimes of all of these modes, there's like, I think 9 modes or something like that here. And they're all above, the lifetimes are 2 milliseconds and the coherence times are 3 milliseconds. So this is like, you know, almost 100 times, maybe 10 or 50 times larger than typical transmon, something like that. And then we have also pretty, and the interaction strengths, we're going to use this dispersive interaction, and those are a few megahertz. So sort of, you know, maybe kilohertz versus megahertz, so a factor of 1,000 there. And it's yeah, quite a bit better than the TD. So so there's a lot of things you can do. So we can do the same thing. We could use these sidebands that we used before. That's one way of controlling it. There's also this idea of you know, snap gates, and then what we're going to talk about is this photon blockade. So we can actually use we can create a effective photon blockade and use that as an interaction, and that was done nicely by Benjamin Huard originally, and we now extend this to a multi-mode photon blockade, which is now creates many body interactions. So in order to understand sort of the plots that I'm going to show you, the way that we measure these things in like this animation there is what's called a Vigner Tomogram. And so that's kind of a way of visualizing states in harmonic oscillators. So you should think of it as an equivalent representation of the density matrix. It's kind of like a Fourier transform. The way that we measure it is by you displace the cavity and then you measure the parity. And I mean, it's actually I'm kind of skipping over it, and it's actually quite interesting how you do that. But but the key thing is that if it's anything that's negative, so like the vacuum looks like this, is a blob, and it has an area of essentially h bar, in the right units. Anytime you see negative something, that means that means it can't be classical. So this is a single photon Fock state. So if you put exactly one photon in the harmonic oscillator, you get that. This is 2 photons, so you can kind of see that Fock states are the number of rings is basically the number of photons. And then you can also make states that are like cat states. So this is like a coherent state plus a coherent state displaced in the opposite direction, and you see that you get these fringes, and so so just to give you a little flavor, and I'll show you most of the things I'll show you will be some flavor of looking like this. And you can think of the x-axis as being like, you can think of this as kind of like x and p in terms of the way it's being plotted. Again, so if you have just a pure cavity, you can only make classical states, because if I go from 0 to 1, it's the same frequency to go to 2. And so if I drive at the 0-1 frequency, at the harmonic oscillator frequency, what I end up doing is I displace it. So I take this vacuum and I displace it. I just move it, but it still looks like vacuum. Okay, so sometimes coherent state is often called displaced vacuum. But now what I'm going to do is I'm going to drive my qubit at that 2 peak. So if you recall, there was there were these different number peaks, and if I drive it at that peak, what that does is it splits this level. And but if it splits the level, now if I go from 0 to 1 to 2, there's nothing there anymore, because I've pushed the level out of the way. And so that creates like a blockade. So I can go from 0 to 1 and it's just perfectly linear. But now if I try to go into 2, I can't. And so what happens is the blob kind of, you can think of it almost as like a wall, and it bounces off and interferes with itself. And that's why you get this negative thing. And you can see it kind of looks like a single photon Fock state. And in fact, a Rabi oscillation. And so this was originally shown by Benjamin Huart a few years ago. You can also, but you don't have to blockade just the second state. You could blockade instead the third state. And now it looks something like a 2 photon state, although not exactly. And so you can sort of make this blockade at whatever radius you want.
If you're driving the transition between G and E, so you should be drawing a line between each of these states.
That's right. But the point is that each of these is actually at a different tuning, because this is at like 2 chi, this is at 4 chi, this is at 6 chi. So, and so this is a big enough difference in frequency, as long as I drive less than chi, that I only hit one transition. And that's sort of the key. So in order to do this, you need to be what's called in the strong dispersive regime. You mean that the dispersive shift is also larger than any of the decay times. So this is an even harder regime to be in than strong coupling, but we were able to do this because the cavity Qs and the qubits are very strongly coupled and very high Q. So you may notice, so this almost looked like that 2 photon Fock state, but not quite, because it doesn't quite look symmetric. And that's because the blockade doesn't give you exactly that when you just by displacing. So, but you can actually use optimal control. And it turns out there's this theory paper that says that in principle it is possible, but they don't give a prescription as to how to do it, that you can make any arbitrary qubit operation with the blockade if you blockade the nth level. But with optimal control, we can just let the computer figure out how to do it. And so now this is how now we can make an exact 2 state. So instead of just a pure displacement, we actually end up displacing something like this, so sort of some extra wiggles. And this is data, so it really, and we can track as a function of time, like the photon number. So that's pretty cool. But what's I think even neater is that we have this multi-mode cavity. So imagine we take 2 modes. So most of the time, the 2 modes will have like different chi shifts. So this is not like 0, 1, 2, 3 for mode 6 and 0, 1, 2 for mode 2. But for example, we can pick a mode. There's ways in which you can actually dress these to change the chi's to match them. But you can also just like, an interesting question is like, what happens if we pick two modes that have the same? So it turns out these two modes have almost identical number shifts. And so that means that if we measure, like, we can't actually tell whether a photon is in mode 5 or mode 6 by measuring the qubit or by blockading. If we blockade, it doesn't actually care whether there's one photon in mode 5 or one photon in mode 6. It just cares that there's never two photons in the system total. And that actually makes an interaction between the modes. So for example, if we drive mode 6, we get a Rabi oscillation, just like we did in the first case. If we drive mode 5, we also get a Rabi oscillation. But now if we drive, if we put a single photon in 5 by, say, doing a pi pulse on it using the blockade, and now we try to drive mode 6, nothing happens. So that's like a controlled, not interaction or something like that. And this is an entangling gate. This entangles them together. And so what you can do is, for example, if this is now multi-mode tomography, which basically is the same thing, except you do every combination of displacements. And because now there's just lots of these diagrams. And to be honest, I don't look at them and have a ton of intuition, other than the sense that you can clearly see that there's correlations. In this case, because it's single photon states, actually the density matrix is better. So like I said, these Vigner tomography is equivalent to the density matrix. So we take the data like this, and then we do some math to get the density matrix. And what you can see is that at the appropriate time, you actually get a Bell state. So like right there is a Bell state. And so you can actually create Bell states between these guys that way. And you can also go to more modes. And the way I like to think of it is you basically, this blockade is essentially like a hyperplane that cuts through, and in this case it's 3D, so it's just a regular plane, but in general it's a hyperplane that cuts through some constant photon number surface. And what's interesting there is it's a pure n photon interaction and also like an n body interaction. So or n site interaction. So there's no interaction below this blockade. So everything looks totally linear. The objects don't interact at all. But as soon as you have n photons, now it is essentially like an all-to-all interaction. And for example, so here we just made another W state. So if with 3, you can also make a W state, and it gets more complicated, but you get the density matrix of a W state. And we've also made, I think, 4 and 5 photon ones, but I don't know, it's not too much. This is already sort of showing that you can do it, but yeah. So anyway, you can make these so it's kind of a very interesting interaction you can make, and it also can allow you to prepare interesting states. Okay, so I think I'm already maybe a minute or two over time, or a couple minutes. So I'll end there, but just our lab does lots of other stuff. So we try to make new types of qubits and protected qubits. We work on autonomous error correction. Turns out actually, I wouldn't have guessed, but qubits are good for dark matter searches. So we're now using the same type of technology to actually speed up the search for axions and dark photons. We're also doing some electrons on helium in our lab. We're starting to see if this type of physics could be extended from the microwave to the millimeter wave range. And we're also doing some hybrid AMO experiments with John Simon. I want to acknowledge all the people who actually did all this work. So first, almost all of this work was done in close collaboration with John Simon and his group. Alex Ma was the postdoc who did all of the Bose-Hubbard physics, along with Brendan and Gabrielle. Clay was the main person behind the chiral insulator, and along with Meg, and then Liang and Wenhao helped a lot with the theory on the multi-mode stuff I just showed you, and Watson led it experimentally along with Andrew and Kevin. So anyway, with that, I'll just put up the conclusions, and if there's any other questions, I'm happy to take them.
Okay, thanks a lot. So are there any questions?
I have a question. So what is the signature of, say, Bell states or W states in the pictures you showed us? What should I focus on? How do you see that there is something special about them?
Yeah, so it's basically in these density matrix. Maybe it's easiest to see in the Bell state. So if you pause it right there where you see the 4 blue squares, so you can see that you've got weight in 1, 0 and 0, 1. And then importantly, there's these off diagonal ones are equal. So that means that it's a coherent state of 0 and 1 and 1, 0, not like just a 50-50 match. So it's basically, in some sense, that you have multiple states along sort of the diagonal, but also that you have off diagonal is sort of the key thing.
So it's basically a tomography.
Yeah. The Vigner, we call it Vigner Tomography. So it's just that basically if you have qubits, this is the natural basis to do things in. But when you have many photons potentially in a harmonic oscillator, it actually is more convenient to measure this by displacing and measuring parity, and you can get the same effective information and then as the density matrix. And so what we do actually is we essentially sample the parity at a bunch of different points, and then that gives us the same information that's in the density matrix. And then we can, if we want to, we can back solve for the density matrix. And if we were, Shai does a lot of stuff with like cats, right? So and cats don't really look very. So these are 0, 0, 1 states, so they look very nice in the density matrix. And probably, in some ways, it's easier to represent it that way. If you're doing cats, it's much easier to see what's going on with these tomography than in the density matrix. It's because it's sort of a coherent state basis, and in general, it tends to be a little easier to measure with this. So either one is equivalent. There's equivalent information, but depending on the type of state you're looking at, one can sort of make it more clear.
But if I look at the picture on the bottom right, what should I focus on?
Again, so first, of course, just that the fact that there's blue there at all means that it's a very quantum state, that it's not some classical just like classical mixture. Also that essentially just that like there's correlations like that in between the angles of these things. But I wouldn't say, for me, I would say these states are most intuitively seen in sort of the upper left picture, because we're dealing with 0 and 1 states. But like if we were to make a cat state, then it would be, the density matrix would be a big mess, because it would have a whole, it would be much bigger. It would, it might have, you might have 5 or 6 photons, and that gets big really quick. And there'd be lots of elements that are lit up, but whereas in this Vigner tomography, it looks like two displaced vacuum states with a bunch of fringes in the middle, and you can sort of read off a lot of things just visually from that. The truth is, of course, as you get into many, the more many-body things get, the more complicated things are, and trying to do brute force tomography just makes less and less sense. So, that's another thing that we're trying to do now in this system is we're trying to figure out ways in which we can directly measure the purity of a state or the Renier entropy of a state, because basically, as you get bigger, the tomography just, it starts to really, it gets really hard to do. So like this took like, probably like, I don't know, an hour. This tomography took, I think it actually took over a day, but I think that's mostly due to like, some inefficient programming. But like, let's say it would take several hours. If we tried to go to a larger state, it would be, start to get prohibitive. So like, so I think, so it starts to be that you actually want to measure the operators you care about directly. So, and which starts to be actually a little bit more like condensed matter physics, ideally.
Okay, other questions? David, can you explain again? I think I missed part of what you explained. So once you generate, I just want to understand again how you generate this entanglement. For example, the simplest case for the 2 modes.
Sure.
So you create this blockade for the whole basically manifold of 2 photons, right?
Right. Yeah. So we drive the qubit at this frequency. Mm-hmm. That basically like splits this level. So essentially, you can occupy this level in either cavity or this level in either cavity, but you can't occupy this level in both cavities because that would be a net that would be 2 shifts, which is equivalent to this, right? So basically you can never have 2 photons in the cavity. And so so now if we drive here, so we're now displacing both of these things, right? So the probability of having no photons is going down. The probability of having photons is going up in both of them. But now what happens is, the probability of having, it doesn't like if we were just driving one of them, it would go up to 1. But now they kind of stop at half, right? Because they can't, only one of these or the other could have a single photon, but not both. And again, and that ends up being this kind of Bell state. And in this case, it's just a simple displacement gives you exactly what you want. In other cases, you might have to do a bit of optimal control to get it to work, but here it's pretty simple.
Okay. So are there any other questions?
Yeah, can I ask a question? It's actually from the last slide, very, very last slide, where you show projects in the lab.
Yeah.
You didn't talk about this, but there's a millimeter wave circuit there, which seemed very interesting. And on like the C subpanel, is that like some high inductance superconductor to give it nonlinearity or something, or?
Yeah, exactly. So that's a little resonator, and it's made out of niobium nitride, and so it's got. And so yeah, if you drive it hard, you can make. We saw that we could get parametric gain out of it, and that paper is published now, so you can grab it off my website. It's
okay. And so, are you thinking of putting like something else there to give it higher nonlinearity to make it into a qubit, or? Yeah.
So in some sense, like what we've been trying to do there is to, we have this whole now fairly well-developed toolbox for circuit QED at 5 gigahertz. Like we know all the commercial suppliers to buy sort of the classical components. We know how to make high Q resonators and in 2D and in 3D. We know how to make qubits in 2D and 3D. So we're sort of trying to build up that, all that toolbox in millimeter wave. And so what we've done so far is we've built 2D resonators like that, and these have Qs of maybe like 50K, 50,000, something like that. And we can. And with kinetic inductance, we can make them weakly nonlinear. We've also made 3D cavities out of a block of niobium. And in fact, that's actually a critical component for this Rydberg experiment, where we actually have Rydbergs trapped in a crossed cavity of millimeter wave photons and optical photons. And there we've shown we can get, I think our record is 30 million Q or 10. We definitely can get above 10. I think 30 might be our record. So actually almost as good at 100 gigahertz as at 5 gigahertz. I was kind of pleasantly surprised there. And so, yeah, so like the clear next thing that we really like to get is a strong nonlinearity so we can make qubits. And we're working on that now. And I would say we think we're close, but we don't know. We have made structures which in principle should work, but we have not yet measured them, and so we're trying to see if it can work. But it's a bit of a challenge because the core of this, as I said at the very beginning, is these aluminum tunnel junctions, and aluminum tunnel junctions have a de facto speed limit at around 30 or 40 gigahertz and a hard limit at 80, which is the gap free, which is just from the gap of the superconductor. So so you really can't use them at 100, but we're hopeful that we can get it to work. And it's
so the nonlinearity you're still doing with the niobium nitride, like nano bridges or something like that.
Yeah, it's not niobium nitride, but it is a nano bridge is the idea. I mean, one could also do it with a niobium tri-layer process as well, but yeah, we're trying to do it with nano bridges. We'll see what happens.
Okay, all right. Good luck. I'll keep an eye out on this.
Sure.
All right, thank you.
Right. Do we have other questions? So I had a quick question. I mean, one thing I didn't understand in this, time versus symmetry breaking part. Why do you want to use a ferrimagnet in particular?
We just want basic, you know, in some sense, what we like the way, and you know, as Aharon said, like you know, the way I think of a circulator is just like a spin that's coupled to a resonator, right? And so what we really want is just the ideal thing would be a macroscopic spin, and a Yig sphere is like kind of the closest thing that is just a big macroscopic spin. You know, right? It's essentially so that they're you know they're coupled together very strongly, so that they kind of are they sort of, at least to first approximation, which even we already see breaking down, they have sort of a mode in which all the spins precess together, so they're all aligned with each other, but they're free to precess. And so it looks like kind of a spin vector that's like got of order 10 to the 20, you know, h bar, and so it's just a big spin that couples well. So that's the reason we like. And Yig is very low loss, and you wouldn't want something that's a hard magnet, because then it'll just like, you know, point in one direction and not move. But
you are talking about an electromagnetic mode, right? Not about motion of any spins, right?
Well, it's a magnon mode, so it is kind of it's the spins that are moving. It's not really. I mean, so I guess it's electromagnetic, but it's really a spin wave that's moving. And
spin wave in what? In vacuum or in a superconductor?
No,
in the Yig crystal. So basically, it's right. This Yig is an insulator, but it has lots of spins in there, and the spins are coupled together, and so. They're strongly enough coupled that they all point in the same direction, and so there's one sort of net spin vector, and then and if you you know, if you excite that, if you put a static magnetic field and it's tilted, it will oscillate, and if you drive it with a microwave, it will start to precess, you know, around, and you know, and there are other modes, of course, so they can either all the spins can be pointing together, or you know, there's another mode where kind of there's, you know, one pole, and you know, like you know, there's all the different, you know, all of the different spherical harmonics of these modes, but we're sort of operating in the lowest one, which is just sort of uniform. And like if we go way back to where we were showing that, you can see that there's other crossings, and those are sort of that approximation breaking down a bit. There's like other spin waves. Here. So there's so like you see there's these other modes coming through. So these are sort of a breakdown of the approximation that this is really like a single spin, just all uniformly pointing. What can actually happen is that, you know, some of the spins can be, you know, there can be like waves of in the spin pointing vector, basically, and those different modes have different frequencies and things like that. So if we were sort of, if this were a more uniform geometry, we would only couple to the uniform mode. But because you can see this is, you know, this isn't the interacting field isn't uniform, and also the bias field is also not uniform, and so actually some of these other spin modes are also coupled in.
Yeah, but you don't want, I mean, the point is that you don't want a hard magnet. You need something to be that kind of magnetization direction can actually become dynamical to couple to it.
Yeah, exactly. Yeah.
I see. Okay, thanks. So other questions? Okay, so I think we've really squeezed every inch of energy out of you. Thanks a lot, David, for getting up early to give you this talk.
No, thanks for having me, and thanks for all the great questions. It's always fun when there's a lot of questions.
And I hope to see you soon in person.
Yeah, no, I would like that. Yeah, I mean, again, you know, and especially in the weather, and you know, and it would be nice. Right now, I'm definitely, you know, wishing I could do that. But more importantly, because it would be fun to talk with everybody.
Yeah. All right, thanks a lot.
Bye.
See you soon.
Thank you. Bye.
All right, thank you.